So 8 was a mess for a lot of people. Not that the composition was the hard part, but I'll tell you what, I saw all kinds of like crazy simplifying done. So I want to state here definitively out loud for now and for all times, this relationship is not true. You cannot break a radical at an addition or subtraction symbol. Many of us tried to do that kind of thing. That's super wrong. Okay? In addition to that, if you had even this, like you can't just like do that and like cancel the radical with one squared thing or whatever. And like I saw all kinds of funky simplifying going on the radical on number 8. The answer you should really have is just 45x squared minus 19 all under the radical, which most people had thereabouts at some point, and then we went ahead and made up our own kind of simplifying. So like, be cautious on that. The other place where I saw a lot of, well, probably the most missed question was 14. Very few people got full marks on that. And the thing that caught almost everybody was when we look at our like standard form for this transformation, the c has to be factored out. So the a here is 3, the c is -1/2, the h is 5. Almost everybody missed that and said the h was -10. Very few people made that or caught that. And those were the two places where I think I saw the most mistakes made were on those two questions. Those are the two that I really want to talk about here. In the next day or so, I'll post my key on in the content library so you guys can take a look at stuff individually. But I want to take a minute and point out those two couple of things there about just like what you can and can't do simplifying radicals. Basically nothing. Multiplication, you can break the thing up, but if there's addition and subtraction under the radical, you are very limited as to what you can do. Okay? And then for that, to identify those values for like A, C, H, and K, you got to make sure that you've kind of factored the C off before you start diving in there to identify the values, because that H can be kind of hiding on you a little bit. Okay, there with those two ideas. Again, if you're not sure on stuff, I'll have my key posted here in the next day or so that you guys can take a look at and you can come back and revisit things. Josh?
Did I ask you like how to do something?
Well, I'll have the key posted here in the next day or two. Yeah, I think so. It's pretty, I think it's pretty thorough. But certainly we can come back and deal with that later if it doesn't. Is that fair?
Yeah.
Okay. All right. Today, let's talk about our plan for the week. Today we're going to close out Chapter 2, looking at Section 2.4. So we'll do our test review day on Wednesday. Friday, I'm going to start Chapter 3 because probably nobody wants to take the test on the day before homecoming. And then we'll just take the test Tuesday next week or whatever our first class day is for Chapter 2. Everybody's cool with that, I hope? Yeah, I feel like that works too. And I'm going to start recording the stuff that's due for the problem set on the board as well as my Notre Dame, just so it's easier for you guys as we kind of get through stuff. I'll add it up or add it onto the list or whatever. Okay. So today will be rather light. We're just going to do one section. It's not that bad. It'll be, we'll finish with, 45 minutes or something probably it'll take to do it. And you can take the rest of the time in class to work on the problem set or whatever. And then next class will be peer review day to work on stuff. And then Friday we'll start chapter 3 or whatever. Okay. Seems cool to you guys? All right. Bueno. You guys made the cripple get up and change or turn off the lights, huh?
Honestly, it's not her legs.
It's not her legs. I'll remember that. Okay. So if you remember, kind of on our first day of class, we had talked about in first semester, one of the big ideas that we're trying to do is to build out these definitions of sine, cosine, and tangent to escape the world of the triangle and kind of build these things out so we can realistically do sine, cosine, and tangent for any angle measure. That's kind of what we're going to be extending through today. So we actually are going to pass through like 2 intermediates along the way, or intermediate steps. So last time we talked about drawing these angles in standard position. So like we have our initial side on the positive x-axis, the vertex at the origin, and then our terminal side, something like that. Everybody's cool there? Okay. So what we're going to do here, or this was actually kind of a big step, because what this did is it took us out of the geometric world where angle measures were bound between 0 and 180 degrees, and into this new world where really you can draw an angle of any size, right? An angle can be up to positive infinity and as small as negative infinity, right? We described how you would do that. So what we're going to do now is we're going to work on, okay, we have this new way of describing angles that allow us to describe angles of any size. How do we do sine, cosine, and tangent in those situations now that we're escaping the world of a right triangle, or even a world in which it's possible to draw any triangle at all? And that's kind of what we're going to be working towards. So let's say we pick some point on this terminal side. Doesn't really matter where that point is. I'm going to just say for the sake of argument, let's say the point is here. I'm going to call that point P, and I'm going to give it the coordinates x, y. I'm going to draw a perpendicular from point P back to the positive x-axis. And what have we made here? By doing that, a right triangle. Everybody see that? So I'm going to refer to this angle here as alpha. So that's the Greek letter alpha. It looks like a fish, like that Jesus fish. And one of the things that we're going to have here is that sine, cosine, tangent, etc. of angle theta is going to be the same as a slightly modified version of angle alpha. So instead of writing sine, cosine, tangent, etc., I'm just going to call it trig. Is everybody okay with that? So when I write capital trig like that, it just means sine, cosine, tangent, cosecant, secant, cotangent, just so I don't have to write 6 different stinking things. So let's just label this. So let's say maybe those, say maybe we have the points P there. We'll call this one here M. And we'll call the point at the origin just O. What is going to be the length for the side MO? Relative to what we've described here. It's got to be X, right? Because to plot the point P, we had to go X to the left. And then the side PM is going to be Y, right? To plot the point P, we had to go X over and then Y up. You guys agree with that? So what we can say then is that, for example, if we take our 6 trig functions, sine, cosine, tangent, cosecant, secant, cotangent, we can now define them in terms of the coordinates of this point P. Almost. There's one more side for P that we forgot to write down. What's the length for PO? How about just the square root of x squared plus y squared, right? It's the hypotenuse of a right triangle, so the Pythagorean theorem holds. The hypotenuse is equal to the sum of the square of the legs. I'm going to call that R, so I don't have to write down all those symbols. Everybody's okay there? Sorry, I forgot that I didn't do that. Okay. So, if I know sine theta is the same as sine alpha is in a right triangle, so I can use SOHCAHTOA there, right? So, sine alpha would be opposite over hypotenuse, or y over r. Cosine theta would be adjacent over hypotenuse, so x over r. Tangent is opposite over adjacent, so y over x. Cosecant is the reciprocal of sine, or hypotenuse over opposite. Secant is the reciprocal of cosine, or hypotenuse over adjacent. And cotangent is the reciprocal of tangent, or adjacent over opposite. So what we've done here is we've translated sine, cosine, tangent, etc., that the right triangle definitions into this standard form angle definition, right? Where x, y, and r are related to a point on the terminal side of a standard position angle. It's a big step. We're getting pretty close to completing these definitions of sine, cosine, and tangent. Let's do a quick example to make sure we got this. Let's say we have the point P that's on the terminal side of theta. And let's say we want to find the 6 trig ratios for theta. So I know here that x is -3. I know that y is 4. And I know that r is the square root of 3 squared plus 4 squared, which is just 5. So far, so good. Sine is y over r. Cosine is x over r. Tangent is y over x. Cosecant is r over y. Secant is r over x. And cotangent is x over y. And I'm done. So far, so good. Pretty easy, right? So these definitions that's something you'd want to have memorized, right? Now, is this definite, or is this any more difficult than SOHCAHTOA is? It's the same thing, except y is replacing opposite, x is replacing adjacent, and r is replacing hypotenuse. But it's still the same definitions, right? Everybody see that? So it's like, yeah, it's something else to memorize, but you don't really have to memorize that much. You just have to remember like those 3 things, and then it's the same as SOHCAHTOA. You know, NBD. What if instead we wanted to find, say, cosine of 150 degrees? So I'll start by kind of drawing our picture. So the vertex is at the origin, initial side on the positive x-axis, 90 and like 60 more. Puts us over here for 150 degrees. So far, so good. So I'm going to pick a point P on the terminal side. It doesn't really matter where. I'm going to drop my perpendicular down and make my triangle here. By the way, this triangle PMO, we call this a reference triangle. And this angle here, alpha, we call the reference angle. In this particular situation, what is the measure of angle alpha? $30 degrees. Why does it have to be 30 degrees? Yeah, we know that a straight line is 180 degrees. We've done 150. It got to be 30 more to get us to the straight line. Everybody's cool with that? So if alpha is 30, then this angle up here has to be 60. And what we really have is a 30, 60, 90 triangle. Everybody's okay there? Well, I know the side lengths for a 30, 60, 90 triangle. X, x root 3, and 2x. But that's not quite right in this situation. What quadrant do you notice point P is in? It's in the second quadrant, right? What is the value of the x coordinate in the second quadrant? It's got to be negative. So I'm going to make this side length that's on the x-axis negative. Since this isn't actually like a triangle with measurements, it's like a representation of an angle measure. It's okay to do that. Everybody on board? So far, so good? Okay. So now that we've drawn our situation, cosine theta is going to be adjacent over hypotenuse. And the x's just cancel out, and we're left with negative root 3 over 2. We good there? Okay. Excuse me. So what's the takeaway here? Well, the takeaway is any of these angles whose reference angle is going to be 30, 60, or 45, we can find the exact value for. Everybody's good with that? So that's great. The next thing we're going to want to do is we're going to want to standardize how we're choosing this point P. So what we're going to do, if we think about this, what we're doing, we have our xy axis, we have our initial side, and as we rotate that terminal side, if we have a fixed point P on that terminal side, what shape are we going to make as it rotates around? What shape are we making as that point P had rotated around? It's a circle, right? So what we're going to want to do is we're going to standardize standardize where P is at relative to the origin. So we're going to make P always 1 unit from the origin. Since P can be any point on that terminal side, we're going to standardize this process and say, okay, well, anytime we pick a point P, instead of just picking an arbitrary point P, we're always going to pick P so that it's 1 unit from the origin. That makes this thing a unit circle. We call it a unit circle because its radius is 1 unit long. God bless you. And what we're going to do on our unit circle is we're going to make a shortcut for the process like what we did here for cosine of 150. Because if we take our unit circle, we know that, say, sine theta was y over r. But in the unit circle, r is just 1. So sine theta is the y coordinate of whatever that point P is. And cosine theta, well, that was x over r. But r is 1, so the cosine is just the x coordinate for P. Tan theta was y over x, but that doesn't change anything. Since r isn't involved, that didn't matter. Cosecant theta was r over y, but if r is 1, we really have 1 over y, or just the reciprocal of the y coordinate. Secant theta is r over x, so 1 over x. And cotangent theta is x over y, but that doesn't change because it's just x's and y's. It doesn't involve r. So this is like our unit circle definition for sine, cosine, tangent, etc. So let's go ahead and show you guys kind of how we build out this unit circle. We're not going to build out the whole thing because it takes a little bit of more time than I'm willing to invest in it, but we'll kind of show you what we're doing process-wise, okay? So we'll just do a couple of examples and be done with it. So let's say we look at 0 degrees or 0 radians. What does the point here have to be on a unit circle? 1, 0, right? The x-coordinate is 1. We've gone 1 over and 0 up. Cool with that? Similarly, we can fill in like 90 degrees or pi over 2 radians as 0, 1. We can fill in 180 degrees or pi radians as negative 1, 0. We can fill in 270 degrees or 3 pi over 2 radians as 0, negative 1. Everybody happy with just running through those real quick? FYI, those are called quadrantal angles because the point or the terminal side lies on one of the x or y axes. Okay, so 30 degrees is the same as pi over 6. If we draw our 30, 60, 90 triangle, we know the hypotenuse of the triangle is the same as the radius, right? So that has to equal 1. So the value for x definitely has to be 1/2. Everybody's okay with that? So this is 1/2, and this is root 3 over 2. Happy there? The left and right is our x. So that's root 3 over 2. And our up and down is our y. So that's 1/2. We saw that 150 or 5 pi over 6 also has a 30-degree reference angle. So it's going to be the same x and y coordinates, except we know the x coordinate is negative because we're in the second quadrant. 210 degrees or 7 pi over 6 also has a 30-degree reference angle. And since we're in the third quadrant, both the x and y coordinates are going to be negative. And then 330 degrees, or 11 pi over 6, is in the fourth quadrant, also has a 30-degree reference angle. So that's going to be positive x coordinate, but a negative y coordinate. Everybody so far so good? The 60-degree angle, well, the x and y's are just going to be flipped, right? If I drew the same triangle with the 60 here, everybody's okay there? So let's go ahead and fill the rest of those in. So that's going to be 120, or, oh, that's pi over 3. And that's 2 pi over 3. So negative 1/2, root 3 over 2. And that's going to be 240. Or 4 pi over 3. And we have negative 1/2 and negative root 3 over 2. And then here we're going to have 300 or 5 pi over 3. And that'll be positive x but negative y. Maybe we are going to fill the whole thing in, I guess. It wasn't that much work. So then we'll do the 45, 45, 90 triangle. So here, again, the hypotenuse needs to be the radius. That needs to be 1 unit long. So x there has to be 1 over the root 2. Everybody agree with that? Because 1 over root 2 times root 2 is just 1. So 45 or pi over 4 radians is just going to be 1 over root 2, 1 over root 2. And then this is 135 or 3 pi over 4. So that'll be negative 1 over root 2 because we're in the second quadrant. And then positive 1 over root 2. And then we're 225 or 5 pi over 4. Since we're in the third quadrant, they're both negative. And then the last one is 315, which is 7 pi over 4. Here the x-coordinate is positive, but the y-coordinate is negative because we're in the fourth quadrant. So that's kind of how we fill out the unit circle, Jackson.
So I realized the unit circle where you do 1 over root 2. I'd always done it root 2 over 2. Would that be fine? That's just getting the root out this time.
Yeah, but it's a little less easier, or a little less, yes, that's fine. Yeah, it's not a big deal. Showing how you get that from this is a little less clear, right, from what we're doing. But that's fine, no big deal. And in fact, the unit circle that I give you that's already printed and filled in everywhere, where you don't have to look at it by hand, has that. Okay, so let's do a little practice using that unit circle here. So I'm just going to copy this over to the notes page. And we'll do a little example, or set of examples here. Okay. So let's say we're asked to evaluate each one of these using the unit circle. Well, I know sine of 120, so I'm just going to locate 120. And then I know the unit circle definition for sine is just y. So I'm going to pull the y coordinate, and that's my answer. I didn't have to build the reference triangle this time or draw the picture, any of that. I just went straight to my unit circle, which all it is just compressing all that work into a set of answers, right? Instead of having to draw the reference triangle and fill in the values and do the 30, 60, 90 triangle, I just can skip all of that work and just pull the value from the unit circle, because we did it once to fill out the unit circle, so we don't have to do it over and over and over again. For tangent of pi over 4, I'm going to locate 5 pi over 4. And tangent, I remember, is y over x. Which reduces down to just 1. And then the last one we're asked to do is cosecant of 390. Well, I notice right away that my unit circle doesn't go up to 390, it stops at 360. So what do I do? Yeah, I'm just going to find an angle coterminal to that by subtracting 360. If the terminal side's in the same position, that point P has to be in the same position. So a coterminal angles are going to have the same values for sine, cosine, and tangent. So now I'm just going to locate 30 degrees, and cosecant is 1 over y, or 2. What do you guys think? Pretty fast, right? Think about how much quicker this was than when we did cosine of 150 by hand, as opposed to just looking it up off the chart and reading the value. It's just a time saver is all the unit circle is, right? It's the same work that we did to do cosine of 150. We're just doing the work once and then recording the results so we can use them over and over and over again. I have one more example problem. And then we can go on about our business. So here we're told that cosine theta is 5/7 and cotangent is negative, and asked to find the value for sine. So let's start by kind of drawing a picture. So I know that cosine is x over r. So my x is 5 and my r is 7. Everybody's okay with that? And since the r is always the radius of a circle, the r always has to be positive. So this couldn't have possibly been -5 over -7 and then reduced down. Everybody's okay with that? If it involves the r always has to be positive. So either I had a situation here or I could have had this situation here. Because those are the two places where the x-coordinate is positive. Everybody's okay with that? How am I going to tell them apart? That's how I'm going to use cotangent for. So I know that cotangent is x over y. Since x was 5, I know that the x-coordinate is positive. That means the y-coordinate needs to be negative. For a fraction to be negative, either the numerator or the denominator have to be negative, but not both. Since I know the numerator is definitively positive because it's x, the denominator must be negative, so the y must be negative. Which means that the triangle we're interested in is this one. So I'm going to go ahead and write a negative sign on that y side of my triangle. And then I'm going to find that side of my triangle using the Pythagorean Theorem. So 24 is equal to y squared. Square root both sides. Remember the square root of 24, I can break that because it's multiplication into the square root of 4 times the square root of 6. Square root of 4 is just 2. So I have 2 square root 6. Everybody happy there? And then lastly then, sine theta is y over r. So that's -2 root 6 over 7. What do you think? One other thing that oftentimes we like to do that makes life sometimes a little bit easier for us is we like to think about what quadrants these trig functions are going to be positive and negative in kind of all at once. So let's just deal with this all now and just record our results so we don't have to kind of think about it every single time. So in the first quadrant, the x-coordinate's positive and the y-coordinate's positive. In the second quadrant, the x is negative, but the y is positive. In the third, they're all negative. And in the fourth, the x is negative or positive, but the y is negative. So I'm just going to record the things that are positive. are the only things I'm going to write in the quadrant. So all of your trig functions are going to be positive in quadrant 1, right? Sine, cosine, tangent, cosecant, secant, cotangent. All of them are positive in quadrant 1. In quadrant 2, it's just going to be cosine and secant. I'm going to just put secant in parentheses because obviously if cosine is negative, its reciprocal also has to be negative. But mostly I'm just going to worry about the cosine because the reciprocal part is easy to remember. In the third quadrant, tangent is going to be positive, right? Y over x is going to be positive, or also then its reciprocal, cotangent, is positive. But all the other ones are negative. And in the last quadrant here, great googly moogly. Yeah, people that are paying attention. Second quadrant is supposed to be sine and cosecant. Good Lord, Mr. Kulik, that was almost a disaster. Everybody caught that I made a mistake there and you fixed it, please? Grace? Of course. And in the last one, this is cosine and secant. So the acronym that they taught me when I was in high school is ASTC, going from quadrant 1 to 4. And we said that all silly turtles crawl. I don't know why. That's what I remember from when I was in high school. You can make up your own acronym to remember that using whatever you deem least appropriate for school settings that I don't need to hear about. Everybody happy? And again, all this is that we did here at the end was just as a shortcut to answer this question of figuring out what quadrant things are in, right? Here, cosine is positive in 1 and 4. Cotangent is positive in, or is negative in 2 and 4. So the one that we need is quadrant 4. Does that make sense? You practice. You'll see what's going on. But basically that's all that piece at the end was doing, was allows us to figure out what quadrant things are positive and negative in without having to really think about it too hard. And if I know what quadrant things are positive or negative in, I can figure out, if I know 2 of them, what quadrant we're dealing with. So that's going to close section 2. So you guys should be able to do up through, or do the rest of the homework sets. That's 45 through 60. You'll notice in the content library I have the blank unit circle that we filled in here together, the nice unit circle that's all pretty, and then I have 2 worksheets for you guys to work on in addition. So this first worksheet is just practice using the unit circle. So these ones should be pretty quick and easy. The hardest part will be like finding the coterminal angle that you need. And then we have some problems like that last example, a couple of those, just to make sure you're good with that. I have the keys attached to them, so there shouldn't be, too much trouble there. And then I have some more transformations practice. We're going to start graphing these trig functions next chapter, so I want to go back and do a little bit more with these transformations, especially after the test and seeing this was still a little bit shaky for some of us. I want to do a little bit of practice there. So again, it's just like identify the values for A, C, H, and K, and then write down the transformations in order. And then there's a little bit more transformation practice stuff going on. And again, I have the key written for all of this stuff, so you don't have, if there's questions or whatever. I'm happy to do stuff still, but I just want to show you all that stuff is in there. Okie dokie. Cool.